Welcome to Regression Part 2 video here, where we're doing a series on regression videos. Specifically, we're going to be using SPSS later, but right now what we want to talk about is sampling variability. So in the last video, we talked basically what regression is, trying to fit a line to some data. And here, Zara collects a sample of 20 observations, and it has the following data with a fitted line. And you can see the line fits pretty good. Now, Ramon also collects a sample of 20 observations on the same thing and has the following fitted line. Notice the data changed between this slide and this slide. Why? Because Ramon has a different sample. Now, I've left the thin line on there to give you an idea of what Zara's sample was as a reference. Okay, now Amir goes and collects 20 samples as well, and he fits a line, and this line is his line, is the darker line, and I've left both Ramon and Zara's lines on there for reference. Okay, Epiphany goes and collects a sample of 20 observations, fits the data, and gets this line, and the other three lines are on there for reference. We've got one more. Jose is going to go collect 20 samples, and he draws a fitted line, which is the darker line, and the other ones are on there for reference. Now notice everybody got a different data set, so that's going to really drive what we're going to be talking about here. Since everybody has a different data set, everybody has a different line, and if we were to repeat this, let's say 100 times, we would get 100 different lines on there. Now, I've taken the data off because each one's going to provide a different sample, but you can see there's a lot of variability in the lines that they fit. You can just see there's one line's way up here and it goes across, and I have another one over here that comes down here. So there's lots of variability in these lines, and that's what we're going to try to monopolize on, is understanding this variability. Now, the red line through here is the true line, and probably none of them actually hit it. I know none of them actually hit it. So what we want to do is some sort of inference on these in specific confidence intervals and hypothesis tests. All right, so let's see here. So the idea of sampling variability again. So sampling variability is how much your answer changes from sample to sample. You take a sample, someone else takes a sample, you all get different values, but likely none of them are the correct value that's for the population. So what we want to do is be able to create a hypothesis test or a confidence interval to actually do something that is reasonably confident that we've captured our value in a confidence interval, or we want to control our ability to make a type 1 error in a hypothesis test. All right, so if I were to take those samples that I just showed you, the lines, and I wrote out their line in a beta 0 and beta 1, these are the numbers that I got off of those. And notice you can see there's a nice distribution here of beta 0 and beta 1. From sample to sample, notice most of them are near this magenta line, and the magenta line is the true value, in this case 5 and 0.5. But they don't vary very far away, but they do not hit the actual value. So that's part of the problem, and we want to monopolize on this. And this is basically how frequentist statistics works. We look at the sampling distribution that occurs across samples, and we try to monopolize on it. So what do? Well, we do know something about the sampling variability. I just showed you a picture. If you look at it, there's a nice pattern to it, right? Seems to be centered at the right value. If we come back, it's centered at the right value, and it seems to be reasonably close to the right value. 4.4 to 5.6 is not that far from 5. And here we've got down here maybe 0.2 to 0.7, and that's kind of close to 0.5. But we'll see, we can actually measure these things, okay? And we can build confidence intervals and hypothesis tests. So we need to start thinking about how regression actually works before we can do anything with this. And I'm going to show you some equations, and in some of the videos I'll actually go over using the equations. Today I'm not going to. I'm just going to show you them to show you that, look, somebody's worked this math out already, and we can utilize it for our analyses. So remember, our goal is to fit a line that has the smallest distance or these errors away from the data. So I have our data, we have these little errors, and we want the line that has the smallest distance or the total errors made. So what we're going to do is, how do we measure it? Well, we're going to measure it just like I said. We're going to use distance. So we're going to measure the point where the line, and I'm going to name the line point here, our predicted value, which is y hat I. So it has a hat on it. This is our estimate of where this point would be. Okay, and this is the actual value, so the difference between those two is what's called the error or the residual. And what we're going to do is just square them and add them up. So I took the actual value, subtract off what I think it's going to be, take that, square it, and then do this for every single one of them and add it up. And now I'm going to divide by n minus 2 because this is the degrees of freedom associated with this situation, and I'll talk more about degrees of freedom later. Just think about it as how much information do I actually have. Now this is going to be called the mean squared error because it's an average of these squared, you can see the squared here, residuals, and the residuals are the errors. So mean squared error. And our sampling variability is related to this because if there's a lot, we miss the data a lot, then there's going to be more sampling variability than if it's really tight. All right, so here's our least squares formula. I'm not going to show you how to come up with them, but if you were to try to do this by hand and you have some data, you have some y and you have some x's, and you can calculate y bar, x bar, you can calculate yi times xi and xi squared, you can get x bar again, x bar and y bar, and you can calculate this by hand. We'll worry about that in another video, but you can do this. And the key here is this is going to give you the same answer as if you did it with a computer. If you're going to do this by hand, start with beta 1 because you need it for this formula. And the hats on the top of here means these are estimators. An estimator is a formula and not a number. Okay, so standard errors. Basically, the standard error is how far do they vary from the mean. Okay, so how much do these vary from sample to sample? And this is why we talked about the mean square error, because it shows up in the formula here. And this is the formula for the standard error of beta 0 hat, and this is the standard error for beta 1 hat. And if you want to, you can calculate these, and this will give you the standard error, which is on your output for most regressions. Okay, and it tells us how much things vary from sample to sample. And the beauty of this is we don't need to do sample to sample. We can do this theoretically, and we can find out how much it will vary from sample to sample. All right, so if I wanted to do a confidence interval, here's my formula. I will estimate beta 0. I'll go look something up on a T table where this is the quantile that I'm interested in, and I have n minus 2 degrees of freedom, and then I'm going to multiply it by the standard error. You've noticed that most confidence intervals look like a point estimate, table value, standard error. That's how the next one looks. We have a point estimate, which is our formula that we calculated, and we know that number is wrong. Plus or minus a table value and its standard error. And then we're hoping that this interval captures the true value C% of the time, whatever we specified C to be. And if we're going to do a hypothesis test, here I'm just doing equals, but you could do less than or equal or greater than or equal, no, it still works out the same. Here, if we're interested in testing beta 0 equals some specific value, then the test statistic is given by this formula here. If you're interested in beta 1, and this is the one we're usually interested in, and we'll talk about that more in another video, this measures, is our test statistic, and it follows a t-distribution with n minus 2 degrees of freedom. You can look these up on the table, the calculated value that you get, and you can get p-values out of it. And then from there, you can use your standard decision rule for inferences. All right, so takeaway. We already understand the sampling variability associated with beta 0 and beta 1 hat. Okay, we already know this, and we can use this to make hypothesis tests and confidence intervals. And that's what's been programmed into your software, and that's what we're going to do in the next few videos. So what we're going to do is look at a data set that has to do with people's coffee intake and the amount of anxiety they have. So we'll do that next, and I'll see you in the next video.